get this show on the road. Actually, we're finished up part 8 in lecture yesterday. Kind of. We're not done with part 8, actually. And so I want to talk a little bit about part 8 before we dive into today's lab. But the other thing, this is actually from part 7. Like, what? So one of the things, once you have your final Lewis structure drawn, you should be able to, the atoms that are connected to other atoms, if it's a neutral molecule that those atoms are making, they should follow these expected valence rules, okay? And so I don't know, I was looking in your lab handout, and I don't see that this is in there. But this is actually one of the checks in today's lab. The valence, the expected valence, is basically the number of times it wants to, I say, reach out, okay? And that actually is both the type of covalent bonds. Remember, sigma bonds are the primary bonds. They're first to arrive. And if you have a double or a triple bond, you're going to have pi bond or bonds. Okay, so honestly, the expected valence is the number of total sigma and pi bonds you expect an atom to reach out. And this is in part 7. Okay, so this is like one of today's checks. It's funny, I've taught this several years, and I'm like, I just now caught this. So, okay, so I'll remind you when we get there. But in the meantime, this slide is actually in your lab background information. Because today, when you draw your Lewis structure, at the end, you're supposed to talk about what we were talking about in lecture yesterday. You're supposed to identify a particular atom, the structural geometry around a particular atom. Now, that's not molecular geometry, that's structural geometry. And I'll remind you, so that's why you're going to get some hands-on today. But what you're going to focus on to understand the hybridization, how that atom has hybridized its atomic orbitals, what you're going to count coming from that atom are two things. You're going to count sigma bonds, and you are going to count lone pair electrons. Those two things. Okay, and then you're going to be able to understand what sort of hybridization that atom has undergone. Now, we aren't going to get into the sp3d or the sp3d2 today. Nope. You will for your homework, just a few. Okay, so the other thing, and actually I have a few slides at the end of part 8. The other thing is, once you know the hybridization, you know these other two columns. Okay, once you know the hybridization, then you know the general geometry, and then you also know the bond angle. So it looks like this. Okay, we could point to that nitrogen atom, and actually this is one of your we're going to go through this. NH3, the neutral molecule, ammonia, we're going to do 4 molecules together, and this is one of them. But this is the final Lewis structure, and that first column on the previous slide, we're supposed to count sigma bonds and lone pair electrons. So, can you see where we have 3 sigma bonds and 1 lone pair electron? So, this is where I say you need to go down to the third row of the previous slide, because you have 4 things that are repulsing from that nitrogen atom. Okay, so in other words, we can answer these questions. It's that nitrogen atom has undergone sp3 orbital hybridization to send out 4 equal hybridized orbitals. We also now know its geometry is tetrahedral. You guys will be making these to convince yourself of that. And the bond angle in any tetrahedral situation is about 109.5. And we're going to talk about that this tomorrow. Okay, in this particular structure, okay, in all of the structures today, I know that arrow looks like it's pointing at the oxygen, but we're going for the central atom. In all the structures today, we're going to identify something as being in the middle. So carbon atom, notice again, if we go ahead and count sigma bonds and lone pair electrons, we have a sigma bond, only one there, and a sigma bond here. So here we're at our middle row, which is 3, and now we can answer these questions. The orbital hybridization that carbon atom has undergone is sp2, structural geometry trigonal planar, okay, and the bond angle, it doesn't look like it. It looks like 90 degrees, but it's 120. Okay. And last but not least, this example where you're like, well, which atom's in the middle? Well, I don't know. We'll just point to one. We'll pick on the chlorine atom. Okay. So again, if we're after this information about that chlorine atom, To me, you gotta count, you gotta count, you gotta count. We have one sigma bond, and oddly enough, remember those lone pair electrons hang out or participate in hybridized orbitals. So we have 4 hybridized orbitals. So that actually is, again, the third row, sp3, orbital hybridization, again, tetrahedral. The bond angle is kind of an odd one because you really don't have the chlorine at a vertex of two bonds, so that's not applicable. So part of getting lab credit for today is going to be this thing, okay? So after you're done with today's lab, there's 2 sides. One side is this, which kind of looks like that, okay? And the other side is to draw Lewis structures. So you turn this in on Monday for lab credit. But what I could ask you, and I might ask you on a test, is I could ask you, point 2, you see I have 4 atoms picked out because structural geometry, electron pair geometry, we're not after the shape of the molecule, we're after around a particular atom, okay? So this first carbon, can you see where it actually has 4 sigma bonds, no lone pair electrons, so that must be, the 2 questions are what's its hybridization and what's the geometry. So that's sp3 tetrahedral. Going over, I think I go clear over to this nitrogen now. So this nitrogen is triple bonded to the carbon, but only one of those 3 covalent bonds is a sigma bond. So we have a sigma and lone pair electron. Sigma, lone pair electron. 1 + 1 is 2. So hey, that must be sp orbital hybridized, okay? And the shape is, the electron pair geometry is linear, okay? Picking on that carbon atom then, the fact that it's singly bonded, and doubly bonded means that that double bond only has 1 sigma bond. So, of course, we have 3 total sigma bonds, no lone pair electrons. So it's sp2 orbital hybridized, which gives that the trigonal planar shape. And like I said, today you're going to be working with models to hopefully kind of convince you of that. That oxygen atom, remember those lone pair electrons, those 2 pairs of lone pair electrons around that oxygen atom are hanging out in hybridized orbitals. So we have hybridized orbital, and hybridized orbital. So again, that's sp2, hybridized, and of course that is trigonal planar. So the same structure, you should be able to kind of get familiar with the bond angle, which to me the bond angle, of course, goes along with the other 2 things we talked about just a minute ago, the orbital hybridization and the shape. So if we kind of pick on some locations of what sort of bond angle do we have. Actually, around that carbon atom, we already said it was sp3 orbital hybridized. We said that's tetrahedral. It's 109.5 is the bond angle there. This carbon atom, we didn't pick on that earlier, but can you see where it has sigma, 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 no lone pair electrons? So 3, that must be the middle. This is how I think of it. That must be the middle row on that important little table that you have. So it's sp2 orbital hybridized, which is planar, 120 degrees then. This one, we didn't pick on this carbon atom before either. Remember, in a triple bond, only one of them is sigma, the other 2 are pi. So we have sigma bond, okay? So we're looking at 2 in that first column, which of course is the first row. So that's sp orbital hybridized is what that carbon atom has undergone, and we say the shape around it is linear, so that's 180 degrees. Okay, so that's kind of what I wanted to do. Now, on to today's, okay? Thank you for bearing with me. So I'm going to pull up, actually, kind of a little template of what we're going to do. So if you would, go ahead and kind of find a sheet that has, yours are actually horizontal. I don't know if I'm saying that right. Yeah. I've gone ahead and made mine vertical. Okay, so if you go ahead, yeah, you should have, looks like page 291. At the top of that, let's go ahead and we're going to do 4 together, and then I'm going to turn you loose. The first one I think we're going to do is the ammonia. And we're going to do those 5 steps that you see. Okay. Cool. Alrighty. So the first step is to come up with the pot of valence electrons. By the way, these steps 1 through 5 actually you already have abbreviated, or I've abbreviated them. You kind of have the full explanation in your packet. So at the top there, let me pick red. The molecule we're going to worry about, do together, is ammonia. Okay. So the pot of valence electrons, I usually do something like this, and this will go in that box. So you need to, all going to do this together. Okay. There's one nitrogen atom. Remember, in order to understand how many valence electrons the group A elements have, what you do is you look at the group number. So nitrogen actually is 5A, so it has 5 valence electrons. Okay, oops. Okay, hydrogen, there are 3, hydrogen atoms. It's atomic number 1, so it has 1 proton and 1 electron, and it's a valence electron. Okay, so collectively those 3 hydrogen atoms bring 3 electrons. So our pot of valence electrons looks like 8. All right. So step number 2, now, step number 2, actually 2 and 3, you're going to kind of come up with a preliminary Lewis structure. The one you're going to put in the middle, and I said it the other day, and it's actually in your handout, the one in the middle is going to be the one with the lowest electronegativity. Our choices are nitrogen or hydrogen in the middle. Hydrogen never, never, never wants to be in the middle. So, with all that in mind, looks like we're stuck with nitrogen. This is a preliminary Lewis structure. Okay, it looks like this. I'm kind of running out of room there. Okay, so that's step 2 and 3. That needs to go in that box. So to get full credit for turning in the lab on Monday, you need to play along with me today. And I will come by and look at pre-lab in just a little bit. So step 4 says whatever electrons you have left over from your pot that you didn't use in these sigma bonds, you can distribute around. Your instructions for step number 3 are to distribute them around the terminal atoms first, and if they're all happy, go ahead and turn your attention to the central atom. That's what your instructions say. So for step number 4, can you see where we had a pot of 8? Okay, that's from step number 1. And can you see we've used up 2, 4, 6? We've used up 6 there. Okay, so the remaining electrons we have are 2. Now our terminal atoms are hydrogen. We should start there, but can you see where hydrogen doesn't want any more? Hydrogen only wants to reach out once in a neutral molecule. That's one thing. But hydrogen is like helium now. Hydrogen is like helium in that actually in this preliminary structure it's sharing joint custody of 2 electrons. Every dash is 2 electrons. Okay? So it's done. So now we turn our attention, we're going to take these 2 electrons and actually go ahead and turn our attention to the central atom. Central atom only has 6 electrons, doesn't it? And it wants 8. So I'm going to redraw this structure over here. Nitrogen, hydrogen, hydrogen, hydrogen. Redraw the preliminary structure. And there are my handy-dandy remaining electrons. So step 5 may or may not apply. Step 5 says look at the central atom, and of course the central atom is nitrogen, and it says if your central atom does not have a complete octet. Well, let's look at our central atom and let's look at how many electrons there are around nitrogen. I got 2, 4, 6, 8. So actually the nitrogen is already happy. So in that box you can write not applicable. Was not required to do it this time. So down at the bottom you see 3 checks and then 3 questions. So the first check is to go ahead and if this is our final Lewis structure, you know, this one right here, this electrons needs to actually match up with step 1. So electrons in step 4 or 5 need to match up with electrons in step 1. So they do. If you go ahead and count we have 2, 4, 6, 8. Okay, and actually that is what we had in step number 1. The next check is, does everything have a complete octet? Or if not an octet, is it happy? And nitrogen has 8 an octet joint custody, and hydrogen is happy because it actually has 2. So yes, we're happy there. And actually, this one, this last check only applies if it's a neutral molecule. It is a neutral molecule. So is it following that first slide I started out with? That's actually a slide from part 7. Number of times it wants to reach out. Well, on that slide, maybe I'll go ahead and put it over here, you saw that hydrogen wants to reach out once. Reaching out once. We know the expected valence of an atom like nitrogen in a neutral molecule if we take 8 minus the group number. Nitrogen is group number 5. 8 minus 5 is 3. So it is reaching out 3 times. And again, these would be, the valence is then the sigma and pi bonds. Okay, so yes, we're all set there. So then we have questions at the bottom. Again, these only apply to the central atom. If you only have 2 atoms, you get a pick. We have an example coming up with only 2 atoms. So for just the nitrogen atom, we need to answer these questions. And to answer these questions, actually, it's going to be, again, back to that whole little table that I said is so important. You know, it's got 2, 3, or 4 with regard to sigma bonds and lone pair electrons. So clearly, if you look at the nitrogen atom, we see that it has 3 sigma bonds and 1 lone pair electron. Okay, so it's got 3 plus 1 is 4. So actually, we must know then it's undergone sp3 orbital hybridization, and then everything else falls into shape. Tetrahedral. Okay, and the bond angle is 109.5, which there is no, and that's degrees. There is no radio station 109.5. I used to be like, oh, that's a nice little radio station. Okay, pass those down. So now is your opportunity to make that molecule. I have 2. Thanks. Perfect. Okay. Now, we're not going to worry about color here. Okay. But I want you, and I'll give you a hint here, you have to, on the things that you're making for the purposes of this lab, you have to show me lone pair electrons. And your hint is just go ahead and make a little white thingy with nothing on the end. So go ahead and see what you can do to make NH3. But again, don't forget those lone pair electrons. Yes. Okay. The second one we're going to do together, and we'll speed these up, trust me. But I want to go ahead and do H2, so it's got 2 hydrogens, CO. So there at the top box, you go ahead and write what we're drawing the structure of, H2CO. So I'm pot of valence electrons. Let's see. With regard to hydrogens, there are 2 of them. They each bring 1 valence electron, collectively 2 electrons. Carbon, there's only 1 carbon atom. Carbon is 4A, so there are 4 valence electrons. Oxygen, there's only 1 oxygen atom. Oxygen is a 6A, so 6 valence electrons. So go ahead and figure out our pot. I got 12 electrons to be distributed. Now the next step, we've got to put something in the middle. It's not going to be hydrogen, so our choices are carbon and oxygen. And if you find them on the periodic table, it goes carbon. Carbon is to the left of oxygen. So carbon actually has the lower electronegativity. So our preliminary Lewis structure would put carbon in the middle and spread the 2 hydrogens out, and you can put them any direction you want, and also spread the oxygen out. So that's our preliminary structure. These kind of go kind of fast once you get started. So underneath that preliminary structure, I'm going to go ahead and take our pot of valence electrons, which is 12, and from that subtract how many electrons we have drawn here on our preliminary structure. Each sigma bond is 2 electrons, so we have 2, 4, 6. So we have 6 electrons there. So we have 6 remaining. So we have 6 electrons to put around the terminal atoms. Hydrogen doesn't want any more electrons, of course, and we're not going to worry about carbon yet because that's in the middle. So we are going to go ahead and worry about the oxygen atom because that's terminal. So here under step 4, I'm going to redraw the structure, central carbon atom, single bond hydrogen, single bond hydrogen, single bond oxygen. And then here's where I go ahead and use those 6 electrons to go ahead and make the oxygen happy. So honestly, it's going to want to hog all 6 of them, isn't it? Because right now in that preliminary structure, it only has 2 electrons. So if I go ahead and take my leftover 6, okay, that all works. Now step number 5 really does need to happen, because on our preliminary structure, you see if we look at our central atom only has, our carbon atom only has 6 electrons. So we did an example like this in class. So this actually is an exciting time where we need to, your instructions are, if you do need to do step number 5, what you do is you look at the terminal atoms and that have lone pair electrons, hopefully. So your oxygen actually has 3 pairs of lone pair electrons. Pick any of those, it really doesn't matter. And I like to kind of show, I circle one and kind of show it swinging in, that's the word swing. Okay, so I can go ahead and redraw this structure over under step 5 now. And it's going to be carbon, single bond hydrogen, and now it's going to be double bond to that oxygen, and that oxygen still has 2 pairs of lone pair electrons. Okay, so by taking one of its 3 pairs of lone pair electrons and swinging it in to form a pi bond, oxygen still has it, and now it shares it with the carbon. Okay. So that should work. Let's take a look. Let's look at our checks. The first check is if you look at that final Lewis structure, do you have the same number of electrons you had in your pot, which was 12? And let's see, 2, 4, 6, 8, 10, 12. I'm counting 12, so that check is good. Okay. The next check is, does each of those atoms have a rare gas configuration, whether that's an octet or for hydrogen that's 2 electrons. So hydrogen has 2 electrons. If we go ahead and draw a circle now around the carbon atom, change the color. If we draw a circle around the carbon atom, okay, you can see it has 8 electrons, 2, 4, 6, 8. If we draw a circle around the oxygen atom, it also has 8 electrons. Does that make sense? Okay. So smiley faces all around. So the next check actually does apply. Since this is a neutral molecule, we expect I'm going to go ahead and put the valence rules up here right quick. In part 7, we have a table, or you have a table in your notes, that says the valence. And again, this is the number of sigma and pi bonds, number of times it reaches out, is 8 minus the group number. And so for carbon, actually it's 8 minus 4, or 4. I'm not going to butcher this. I'm going to grab a periodic table. So if we look at 5A elements, nonmetals, nitrogen and phosphorus, okay, 8 minus 5 is 3. If we look at oxygen, sulfur, and selenium, those are 6A, 8 minus 6 is 2. And then if we look at the halogens, chlorine, bromine, iodine, okay, 7A, so 8 minus 7 is 1. Okay, that's the number of times you expect them to reach out. Hydrogen, expected valence is 1, and I think we had boron on there. The troublemaker, who doesn't want an octet, it wants 6. And so actually its expected valence in a neutral molecule is 3. Okay, but remember, and sometimes we'll forget this, this is in neutral molecules only. We are going to do some Lewis structures involving covalent bonds and polyatomic ions like sulfate and such, and they don't have to follow the expected valence rules. So let's take a look at our Lewis structure. And can you see where carbon is reaching out? Okay, it's got 3 sigma bonds, 1 pi bond. 3 plus 1 is 4. Its expected valence is 4. Cool. Oxygen. Okay, it's got a sigma and a pi bond. It's reaching out twice. Its expected valence is 2. Cool. expected valence of hydrogen is 1. So yes, smiley faces all around. The last part, again, I have to tell you which atom of interest. In this case, it's the central atom, the carbon atom. So in order to answer these questions for the final Lewis structure, we look at sigma bonds and lone pair electrons. So can you see where that carbon atom has 3 sigma bonds, no lone pair electrons? So it's the middle row. Okay, so it's sp2 orbital hybridized. Okay, and then the other things kind of fall into place. The structural geometry is trigonal planar. And of course, the bond angle associated with that works, and it's 120. So what I'm hoping, 120 degrees. So go ahead and make this and see if actually you can see this last part around that central carbon atom. And this one, I'm going to throw a little twist in it. Actually, this is one of those polyatomic ions, okay, running around with a negative charge. Are you like me, the whole halogens, the oxy, they drive me nuts. So we're going with hypochlorite, ClO minus. ClO with a -1 charge. Okay, so how hard could that be? So actually we only have 2 atoms to stick together. Chlorine, the pot of valence electrons, there's only 1. It's a 7A element. Oxygen, there's only 1. It's a 6A element, so 6 electrons. Okay. Now this is where I usually put the word charge. Okay, and the fact that it's got a -1 charge, okay, means that actually it has 1 extra electron. If it was -2, we'd kick in 2 extra electrons. So 7 plus 6 plus 1, I got 14 electrons to be distributed around that hypochlorite ion. All right, the next step, usually we find what's going to go in the middle. But if we look at where chlorine and oxygen is on the periodic table, actually we're going to kind of, even though there's no middle, oxygen has a lower electronegativity, so we're going to kind of pretend that that is our central atom. Okay, it's kind of dumb, right? So just bear with me. So we're going to call that central for purposes of kind of doing the next part. So that next box just has that 1 sigma bond between those 2. And let's go ahead in that box or the next box. So the leftover electrons from the pot of valence electrons are a lot, right? So we had a pot of 14 from step number 1, and here in our preliminary structure we've only drawn 2, used up 2. So actually we have 12 electrons to do something with. And you know what? I'm thinking this is going to be a beautiful deal. So I'm going to redraw on step number 4. I'm going to redraw our preliminary structure, which is chlorine, sigma bond, oxygen. And now I'm going to distribute those first around the terminal atom. And that's the chlorine atom. It only has 2. And if it wants 8, needs 8, then I got to take 6 of those 12. Okay, so I'm now down to only 6. But you know what? That should work just fine. Does that make sense? Yeah, I think so too. So we actually have used up all our pot, and both of those atoms have a complete octet. Now, I'm going to show you one more thing if you want to get full credit, and I know you do, that's kind of a dumb question. Okay, in order to get full credit for that Lewis structure, you have to show that it's running around with a -1 charge. And the best way that I want you to do that is basically collect it and put the sign of the charge outside. Okay? So then you're done. So if our central atom was the oxygen atom, of course, it does have a complete octet. Okay, so Na for step number 5. Now let's go take a look at our checks. So the first check is, do we have 14 electrons there? 2, 4, 6, 8, 10, 12, 14. Yes, we do. Does each, the chlorine and the oxygen atom, have a complete octet? Yeah, they do if they share those 2 electrons in that sigma bond. If this is a neutral atom, stop right there. This check does not apply, need not apply. Just for kicks, if we look at the expected valence of chlorine in neutral molecules, it's 1. We look at the expected valence of an oxygen atom in a neutral molecule, and it's 2. Okay, but that's okay because it's not a neutral molecule. So we picked randomly oxygen as our central atom. So let's go ahead and answer those questions about the oxygen atom. Okay, so the oxygen atom. So in order to answer these questions, we have to count sigma bonds, which there's 1, and pairs of lone pair electrons, which there's 3. So 1 plus 3 is 4. So when you put this, make this little Lewis structure, what you're going to see is kind of strange, maybe, maybe not. We have that oxygen atom has undergone sp3 orbital hybridization. Its structural geometry, we said, is tetrahedral. And since there are not 2 atoms kind of coming off from the oxygen atom, it doesn't make sense to talk about a bond angle. But if you're going to kind of talk about the angle between an electron domain and the sigma bond, it'd be 109.5. But not applicable. Okay, go ahead and make that structure. So at the top there, on your 4th box, go ahead and write N2. How hard could that be, right? Okay, so nitrogen. There are 2 nitrogen atoms, and nitrogen is a 5A element. So they each bring 5 electrons. So we have 10 electrons that need to go ahead and give each one of those nitrogen atoms a complete octet. You're like, okay, 10, 8, how does that work? It'll work just fine. Let's still go through these steps. The next step we said was to draw the preliminary structure with that, in this case, just 1 sigma bond between the 2 nitrogen atoms. So the next box has nitrogen, sigma bond, nitrogen. So in that box, or in the next box if you want, if we go ahead and take the pot of electrons, which was 10, and from that subtract the number of electrons we've used, okay, we have 8 electrons to go ahead and distribute around the terminal nitrogen. So if you don't mind, kind of like we did with the previous structure, let's just for kicks call this one our central. We'll call our right one the central one. So we're going to leave it for last. And we'll call our left one the terminal, just so we're all on the same page. So we're going to go ahead and satisfy the left one first. So redraw our structure, nitrogen, single bond nitrogen. Okay, and we're going to make that left one happy first. Well, it needs 6, doesn't it? If it's only got sharing a pair of electrons, so to get 8, it needs 6 more. Okay, so of our leftover electrons, I've used 6 of the 8, so I have 2 electrons to go ahead and put on our central nitrogen atom. Okay, that's pretty good. So the last step, actually, in playing the game this way, we definitely need to fix that poor right nitrogen. No offense, right nitrogen. So we can fix it. If it only has 4, actually it needs 4 more. So this is a case where we are, to get 4, we're going to take 2 pairs. And I took them from the north and the south. Didn't have to be from the north and the south. But I'm kind of showing the swinging. So if I do that, let's go ahead and under that last box, redraw our structure. Now we have nitrogen, sigma, pi, pi bond. The other nitrogen, we had 2 electrons coming along for the ride on our left one, and actually 2 electrons coming along for the ride on our right one. That's it. That actually is how molecular nitrogen runs around. Okay, so let's do our checks. So we had a pot of 10 electrons in step number 1. Notice we have 2, 4, 6, 8, 10. We have 10 electrons on our final Lewis structure, so that's cool. We're looking for a complete set of 8 electrons around both of the nitrogen atoms. And actually, if they share 6, good heavens, they are sharing sort of atoms. Okay, if they share 6 and they have 2 of their own, yeah, they have a complete octet. Since this is a neutral molecule, there's no overall charge, we would expect it to follow the rules. Okay, and since nitrogen and phosphorus are both 5A, 8 minus 5 is 3. Remember, when we talk about the valence of an atom in a neutral molecule, that's the number of sigma and pi bonds. Has 1 sigma, 2 pi. So 3. So yes, it's symmetrical, so honestly it doesn't matter how we answer this question, but let's go with the right one. It really would not matter. To understand the hybridization that either nitrogen atom, but this right one has undergone, the 2 things we count, and that's the first column in that table that is in part 8. The 2 things we count are the sigma bonds and lone pair electrons. So can you see where the number of sigma bonds is just 1, because those other 2 are pi, and the number of pairs of lone pair electrons is also just 1. So 1 plus 1 is 2. So we're going with the first actually row in the 2, 3, or 4. So the orbital hybridization is sp, and the other 2 things kind of fall into place. So we said the structural geometry is linear, and the bond angle, I always think of a hot dot when I think of linear, but the bond angle is 180 degrees. Make that structure. So here, actually, your ticket out of here is to go ahead, and those are the 6 that I want you to do. And when I say do, that means like take this structure and go through all the steps, including the checks and the hybridization, and then also make the physical ball and stick model of it. And you can work together, work on your own, okay? But when you're done and you have your 6 structures and you have your papers all filled out, I'll come around and take a look at them and give you the sheet. Any questions? I love those molecules.